I'm Jamie Gwynn. I'm a volunteer here at the Clarkdale Historical Society. Before we get started, I want to let you know that there are bathrooms. After you go through the first door, they're on the left. At least the women's room is. I don't know where the men's room is, so. And also, if everybody would take a moment to silence your phones before we get started. Turn the ringer off. And yeah, welcome. We have a really great show for you today. Hal Hatfield is here, and I'm just going to tell you a little bit about him. He grew up in upstate New York. He got his bachelor's degree in geology from the State University of New York at Potsdam, which is over by Massachusetts, I just found out, and his master's degree from Idaho State University. He also has a graduate certificate from Utah State University. Before retirement, he spent over 35 years as an environmental scientist, geologist to be specific, conducting and managing hydrogeologic investigations and remediation at contaminated sites. So it was helping clean up the contaminated sites. Site remediation included work at gas stations, Superfund sites, Department of Defense, and Department of Energy sites. Hal currently volunteers at the Jerome State Historic Park as an interpreter of Verde Valley geology, mining, and history. He also leads classes for Ollie in the history and geology of the Verde Valley here in Clarkdale. Today, he'll give us an overview of the geologic history of the Black Hills and Verde Valley, including the early history of how the copper ore bodies of Jerome were formed, the geologic formations that developed over the ore bodies, how the Black Hills and the Verde Valley were created. Spoiler alert, geologically, we are not a true valley. And the volcanics that covered everything. Please welcome our very special guest, Hal Hatfield.
Thank you, Jamie. Appreciate the intro. Hal Hatfield here. Let me go over some of the show and tell things I brought. So in front of us here on the table, we have some samples of some of the rocks I'm going to talk about today. We're going to have the Tapeats sandstone, there's the Martin Formation, there's a red wall, we're going to talk about the volcanics, the Hickey Formation, and we're going to end up with the Verde Formation, our newest formation. So some of the other things I brought here is we have a stratigraphic section. After we were done with the talk, please come up and take a look, showing the rocks we have from the earliest down to the oldest. So the oldest on the bottom. And we're going to talk about this lower half here is what's called the Precambrian rocks. So they're referred to as basement rocks. And then these are rocks that developed on top of them. Next down the line here, we have a cross-section of the two mines, the United Verde Copper Company on the left and the United Verde Extension on the right, with the Verde Fault that splits the two. And then to the far right, the one on top is for the United Verde Copper Company, kind of a cross-section of where their tunnels are, the shafts, and where the ore body is in relation to it. And down on the floor, we only had 3 easels, so that one's down on the floor. The one on the floor is the United Verde Extension, and that is underneath the Jerome State Historic Park, where I volunteer. So, geologic history of the Black Hills and Verde Valley, a condensed version. I believe, by looking at our crowd here, you would understand that when I say this is the Reader's Digest version. If we had a younger audience, maybe not so much. Okay, so this is Verde Valley. We have Sedona to the northeast, Camp Verde, Rim Rock to the southeast, Clarkdale to the northwest, along with Jerome and Cottonwood, and Cornville in the middle. So this is what everyone refers to as the Verde Valley. Geologically, it's not a valley. So our objectives today, we're going to learn what this place is that we live in. We're going to talk about the different types of rocks that are present in our area. We're going to learn some key geologic events that lead to the creation of our three towns here, Jerome, Clarkdale, and Clemenceau. And there are actually going to be two main geologic events: the formation of the ore bodies and the exposure of the ore bodies. And then we're going to have a little overview of some of the rock formations in the Black Hills and Verde Valley that you see every day, or if you take a drive from here up to Mingus Mountain. Okay, so officially you're welcome to the Verde Tilted Half Graben. Geologically, that's what we are. When you think of a valley, well, a valley is formed by water. And so if it's a new valley, it's going to be a V-shaped. This valley that we call a valley is a basin. And it's technically a tilted half graben, which we'll get to in a little bit here. So valleys can be formed by water or ice. If it's formed by ice like a glacier, it's going to be U-shaped. If it's formed by water, it'll be a V-shape, which flattens out over time. Come on in, folks, we've got more room. Okay, so we have to learn a bit about our rocks. We have three types of rocks: igneous, sedimentary, and metamorphic. All this you should have learned when you were in school, and hopefully you retained some of it. But we're going to go over the different rocks as we move along here. Some definitions. Key definitions: a rock. A rock is a naturally occurring and coherent aggregate of one or more minerals. And there will be a short quiz later, so try to remember this. Igneous rock, one of the three types of rocks, are formed by solidification of magma within the earth. It's either intrusive or extrusive. Example of an intrusive rock would be granite, like you see over to Prescott area. The thing with that means intrusive, it has not broken through the Earth's crust. Therefore, it has time to slowly cool, and when it does, it forms crystals that are fairly large and visible by the naked eye. Whereas an extrusive, they cool really quick, and you can't see crystals to speak of. Igneous rocks. So our crust, Earth's crust, is composed of 64.7% igneous rocks. So that's our main rocks, with 7.9% sedimentary and 27.4% metamorphic. Igneous rocks are divided into two categories, which I already mentioned briefly. We got the intrusive, and we have the extrusive, which is referred to as lava when it comes to the surface. An extrusive doesn't necessarily have to be on top of the crust, but it can be in the ocean too. More definitions. Sedimentary rock is formed from liquefaction of sediment or precipitation from solution or consolidation of plant and animal remains. So examples of liquefaction of sediment, we have sandstone here on the end of the table, the Tapete sandstone. Precipitation from solution, good examples would be limestone, red wall limestone, and a consolidation of plant animal remains. That would be coal. We don't have coal here, so we're not going to show that one. Sedimentary rocks deposited and lithified, already mentioned that, with the assistance of running water, wind, ice, organisms, deposited in the land surface to the bottoms of lakes, oceans, and rivers. The Tapete sandstone, which we're going to talk about a little bit later, that was deposited in tidal flat areas, so it'd be shoreline deposition. And sedimentary rocks are generally stratified. They have layers, and you'll be able to see different particle sizes, particularly in the tapetes. And they're the most common rock type on the Earth's surface, even though the Earth doesn't have percentage-wise a lot of them. One last definition, metamorphic rock. So this is a rock that's transformed from previous existing rock. So it can be a sedimentary rock, it can be an igneous rock, It can even be another metamorphic rock, which is hard to differentiate. Okay, so now we're going to talk about the three physiographic provinces and the differences. We live in a transition zone. Let's see. Oh, wrong way. There we go, right there. About where that, right out there. And so what we have is a transition zone has factors of both the basin and range and the Colorado Plateau. And when we zoom out, you can see how large the Colorado Plateau is here. It covers 4 states. And the basin and range goes all the way from New Mexico, southern Arizona, covers a good part of northern Mexico, southeastern California, all of Nevada, western Utah, and southern Idaho, and southeast Oregon. So it's a big province. And we're going to talk about how that was formed and why it's important here in a little bit. So, everybody in the back, read this. I believe this lady here told me not to put this slide in because no one would be able to see it. But it's important in that this is the geological time scale. And what this is showing, you can come up and we can look at it later, but wrong way, wrong button. So the bottom part here, these oldest rocks are in the bottom. The same for over here, the oldest rocks at the bottom. And they're referred to as basement rocks because everything else is built upon them. So above it, we have the Paleozoic rocks. We have the Cambrian, Ordovician, Silurian, etc., up through here. So these are different time periods. There's eons is the first time period. There's eras, periods, and epochs. The center part here is life forms, what was going on during the different periods. And on the far right is North American events. So if you have a real interest in this slide, I got it from the National Park Service. You can just Google it, and it's really comprehensive. It's a good little reference to have. Okay, so formation of Earth, 4,600 million years ago, give or take. So before Arizona rocks were formed, a good 60% of the Earth's history has already gone by. So these rocks are 1,750 million years old. And they're referred to, like I mentioned earlier, basement rocks. So United Verde Extension and the United Verde Copper Company ore bodies are in these basement rocks, and they are in the lower Cleopatra rhyolite. That's where they're formed, and that's where we're going to talk about here momentarily. But first, we have to talk about plate tectonics. If you remember, oh no, a lot of you graduated before plate tectonics even came out. Plate tectonics was from 1960s. That's when the theory came up. It's a theory about how the Earth's lithospheres divide into a series of rigid plates, it's how they move about and forms of volcanoes and mountain ranges. And lithosphere, in case anyone's interested, is the outer part of the Earth consisting of the crust and the upper mantle, and can be as much as 62 miles thick. So it's created in the mid-ocean ridges, which we show right here, right there. So it'd be created coming up from the mantle, and then it's going to go down into the trenches and be assimilated back. So it's a cycle, how the rocks are formed. And this is moving, these trenches, the plates are moving approximately 3 centimeters per year. So we're on the North American plate. And at one point, it was down at the tropical areas and moved up this way. And at 3 centimeters a year, we were heading westward. And that is equivalent to your fingernails, the rate of your fingernails growing. So we're still moving, and we'll be moving for some time. So here's another schematic of plate tectonics showing where you have your plate, the formation of the ridges here. We are at a subduction zone. This is where everything happened here for us. So we had one plate going underneath another. And we have island arcs. There was two major island arcs that formed. Another schematic of them. So we had two island arcs that came into the main body of the continent that was existing. And the subduction, and then they're pulled in. And at this time period, this is 1,750 million years ago, this is going to be the formation of the ore bodies up in Jerome. Now, everyone memorize this slide. There's a lot going on here. This is just, we're going to talk about the basics. Volcanogenic massive sulfide deposits, VMS deposits. VMS is really important to Jerome. This is what created the rock bodies. And so we had, I'm going to go to this one here. This is a better schematic for this. At that time period, we were about 2 to 3 miles below the ocean on the ocean floor. The plate was, one plate was going underneath the other. We were getting volcanoes coming up. We had a large volcano here that was 6 miles in diameter. It's called the stratovolcano. And that blew, and we had a big crater. And when that crater was formed, you're getting the hydrothermal vents coming up from the mantle. And what that's doing, it's superheating all the water in the ocean around it. It's kind of like if you have a pot of water boiling on the stove, you get the convection currents. In this case, what that convection is doing, the superheated water, is it's leaching out the metals in the rocks around it and bringing them up into what's called black smokers over here. So these are sulfide-based minerals. We have, besides sulfur, you're going to have copper, you're going to have lead, you're going to have zinc, gold, silver, other metals. And they're formed into bands. And so the two ore bodies we have, United Verde Extension and United Verde Copper Company up in Jerome, were two of the bands. There are other bands through the Black Hills. They haven't been developed. Whether they will be in the future, only time will tell. Okay, this is a picture from a geology exhibit up at the Jerome State Historic Park at Douglas Mansion. So what this is showing is you got different letters and numbers, and you can look, you go up there, there's a geology room in the mansion up there, and you can identify the rocks based on those letters and numbers because there'll be examples of each of those. So if you want to know what's going on right in the heart of the black smoker, you look up 6A. You want to know what's going on the edge, over here 7B, you can look it up. And you get different examples. So this is where our copper and gold are. Okay, so we're going to talk briefly about the Paleozoic era. So we know when the ore bodies were formed. We're going to get to a point where the ore bodies are exposed because they're deep in the crust right now. But first we got the Paleozoic era, which is, as you can see here, 570 to 245 million years ago, often abbreviated as MYIA or MY in documents. So between the basement rocks being formed and the Paleozoic era, you have 900 million years of nothing. As in, we have no evidence here or the Grand Canyon or anywhere in the part of the U.S. where anything was deposited or eroded away. There's just no evidence. The Paleozoic era starts at 570. Arizona at that time on the North American plate was close to the equator, moving up this way. We had streams that began depositing the Tepete sandstone. So the Tepete sandstone is our first deposited rock after Precambrian period. And also Chino Valley mudstone. I don't have examples of that. So that's our first rocks being deposited. And then after that, sedimentary rocks that is, we have the Devonian Mississippian periods where you're getting carbonates. You're getting the Martin Formation and red wall limestone. And the red wall limestone, we have example here, and the Martin Formation. Let's see, they accumulate to depths of 690 feet. Pretty thick sediments. And then above that, we have the Supai sandstone, which is not very thick here. It's up to 100 feet. Those are the red rocks you see in the distance, up on the hills above Jerome, over in Sycamore Canyon. The red rocks of Sedona are primarily Supai sandstone. And the thing is, with the red wall, it's right below it. And generally, limestone is usually whitish or gray in color, but the red wall limestone has been stained by the iron that's in the Supai Formation. Okay, so I talked briefly about the ore bodies being formed. Now I'm going to talk briefly about how they're exposed so people know where to look for them. And that's the Basin and Range. So, Basin and Range time period is 20 million years ago. The crust of the Basin and Range is being stretched. So what's happening, you've got two plates that are pulling apart. And when they're pulling apart, the basins are going to drop down. And there's over 400 mountain blocks. I remember a professor at one point looking at a satellite image of the Basin and Range province. You saw how extensive it is. He equated the 400 mountain blocks as caterpillars marching north. It's a neat analogy. Okay, so the Basin and Range crust is stretched up to 100% of its original width. Here is a diagram of it. So Basin and Range is also called horst and graben. This is where the tilted half graben comes in. So when it's pushed up, the mantle is pushing up, and that's the horst or range. And then when it's being pulled, you're getting the downdrops of the basins or grabens. Horst and graben are German terms. And then you can have tilting of the blocks. And this is a 1966 cross-section that's actually done by a geologist from Mingus Mountain over through the other side of Grand Canyon. So I just blew up the one section here. And you can see where we're at. Here's Mingus Mountain here. And we're down here. And the thickness of this area here is 6,100 feet. There was drilling done by the mining companies back in the 1970s that confirmed the depth of this side here. So if you remember, we're in the transition zone. So we're at the very edge of the Basin and Range before we hit the Colorado Plateau. So over here in the Colorado Plateau, where you got the Mogollon Rim, this is acting as a hinge. And so this area over here is downdropping to the right, the 6,100 feet. And this is why it's called a tilted half graben. So you can see it's tilted based on the Verde Fault. And you can see it's only a half a graben. So we're in the Verde tilted half graben. Doesn't roll off the tongue, but it is what it is. Okay, what is this? Remember, I gave you a definition of a rock. So that material there is a coherent aggregate of one or more minerals. Specifically, it's got a lot of iron in it and a lot of silica. But it is a rock, based on our definition. No, it's not naturally occurring. It's slag. It's not classified as a rock. It's a byproduct of the metal smelting process. And it resembles a rock. It's got density of a rock. It's denser than many rocks. I wouldn't want to be hit by one of them. But it's a man-made material, so it's not officially a rock. Okay, this is a rock. This is over in the Grand Canyon. This is the first sedimentary rock to be formed above the basement rocks. Depete sandstone. It's a ledge-forming formation. It's from tidal flats, the shorelines. Here, if you're driving up 89A towards Mingus Mountain, and if you look to the right as you're driving up, well, you got to be a passenger to see it because you should be looking at the road, those hairpin turns. But you can see the reddish-brown sandstone. And it's a sandstone and conglomerate as well. Next one we're going to talk about briefly is red wall limestone. Again, this is in the Grand Canyon. And Grand Canyon's been documented thoroughly as far as the geologic formations over there. And what we have is a thinner version over on our side. Okay, so why did I throw this in here? Well, the red wall limestone is behind here on the hills, but this facility here, the cement plant, is using the red wall limestone. The red wall limestone is 99.5% pure limestone. It has very little silt or sand or other debris in it from other rocks. So if you know your history of our cement plant out here, this was built in 1959 for the sole purpose of providing the cement for the Glen Canyon Dam. So from 1959, for a period of about 5 years, they were making cement out of it using the red wall limestone, and they're taking it in trucks. Every 15 minutes, a truck would drive round the clock up to Page to build the Glen Canyon Dam. And it's obviously used to this day. You'll see all the different semi-trucks, the tankers going up I-17. They're going down to Phoenix. So the red wall limestone is a fossiliferous limestone. And one of the main fossils is this guy here on the left. It's a crinoid. And they're still existing today. Here's a live one over here. Well, a picture of a live one. They're beautiful. They're related to the starfish and sea urchins. And I got a couple examples here of the red wall limestone that you'll see these little segments here. They look like little, if you know what Smarties look like, the little candies, they look like there's stems. So in the red wall here, it's not going to be a perfect example of what the crinoid body and flower would have looked like, because it's referred to as fossil hash. What happened is the seas got turbulent and it disturbed all the fossils that were down there. So they're all broken up. So you'll see some segments in the example I've got here. Okay, a little bit of volcanic activity in the Verde Valley region. Oh, Verde tilted half graben, sorry. We got the Hickey Formation, which I get an example of over here. It's on top of the Black Hills. 10 to 15 million years ago, came up through various fissures and vents. And it would be a slow-moving, just widespread blanket of volcanics, kind of like House Mountain. Does everyone know where House Mountain is? If you're in Cornville and you're looking towards Sedona, House Mountain will be in your way. It's a rounded mountain. It's a shield volcano formed about 14 million years ago. It's like the volcanoes over in Hawaii. It's because it's low viscosity and low silica content, so it just flows naturally and smoothly, as opposed to the Hackberry Mountain, which is southeast of Camp Verde. That was a stratovolcano between 2.2 and 3.9 million years ago. That one has high viscosity, high silica, and what happens with that, it gets to a point where it goes like Mount St. Helens does. It just blows up dramatically, and that happened 2.2 to 3.9 million years ago over in that part of the valley. And there was a lot of geologists early on thought the volcanics from Hackberry Mountain dammed up the valley, tilted half graben, see, I had the bad habit, and formed a big lake behind it. This lake, Verde Formation, 10 million to 2.5 million years ago. So it was around for a while. This is a road cut from Interstate 17, courtesy of our good folks at DOT. And what this is a series of, let's see, I had to jot this down. There's so much going on at this. We have multiple layers of limestone, mudstone, some conglomerates, sandstones, evaporites, and interbedded layers of volcanics, all in this area here. It's 3,100 feet thick, and it is 300 miles in extent. So it goes from 10 miles northwest of Clarkdale to around 10 miles southeast of Camp Verde. So it's pretty extensive. And here we have a cross-section showing the deep water area here in the center. We have alluvial fans to the west coming off the Black Hills. Off the rim itself to the east, we have some mud flats. And the good examples of this is over at Dead Horse State Park. There's a lot of good examples of the rock. That's where the example, don't tell anyone, that came from the park. I forgot to ask them. But there's other fine examples around. And I believe I've whipped this pretty quickly. So the Verde tilted half graben thanks you for listening to some of its story. So I can expand on anything that people have questions on. So
If you have a question, please raise your hand.
we have one over here. Going to make you walk for it.
Yep.
We're going to use the microphone so other people can hear what the question is. Will I have the right answer? We'll find out. Bingo. Thank you.
If you stand upriver from Clarkdale, right by the Verde River, and you look, I guess that would be north, you get the red wall stuff up there.
Right.
There's an area where it's white, and then there's kind of a diagonal where everything turns white, goes back to red. And I've been told that was the extent of ancient Verde Lake. Is that
That
correct? True?
Yes. Yep, that would be what we just saw here. Yep, exactly.
Thank you.
Mm-hmm. Yeah, that'd be Sycamore Canyon area. Up here, Michael.
In the slide of the Tapeats sandstone that you showed, it looked like that was sitting on top of some white rock underneath it.
Well, let's take a look.
If so, what is that?
Let's go back to Tapeats. Okay, that's just the weathering. That is also Tapeats on the bottom.
Okay.
It's just because the creek goes through there, the Hermit Creek, and it's just calcium carbonate buildup,
Yeah.
hard water.
Thank you.
Yep. Got one in the back, Michael. Looks like literally it's standing room only today.
So plate tectonics, I thought it was an established fact. You said it's a theory. What confidence level do they have in that theory?
Plate tectonics, we'll go back here. Further back than I thought. Okay. With the advent of GPS, they can go down to the gnat's hair as far as the movement. That's how we know there's 3 centimeters per year the plates are moving. And they have been able to verify through the GPS, through fossils, because they can see fossils, say for instance over in England, that match fossils over on the northeast coast of the US. They're the same type of rock. So they know they've been split somehow, and they couldn't figure out how to split, and somebody came up with this ingenious idea of the plates actually moving. And just over time, they've been able to, I don't know if it's still considered a theory or if it's a fact now, but everyone believes it's a fact, if it's not.
So a high confidence level then.
Yeah, it's a high confidence level, yes.
Thank you.
Yep.
I believe that one of the confirmations of plate tectonics was due to some core samples that were taken on either side of the Mid-Atlantic Rift.
Correct.
And that showed magnetic variations as they went deep.
Right.
And thus confirming that they were deposited at different times as it spread.
Right on the nose on that one. I didn't have to answer a question. Thank you. I like those
Hi.
kind of questions.
Yeah. Could you differentiate between the Verde Formation and the Kaibab limestone and the extent of those two apparently different water bodies?
That would have been different, yes. The Verde Formation is fresh water, whereas the Kaibab limestone would have been in a sea. And so, yeah, they're different locations and at different time periods. The Verde Formation is much younger than the Kaibab limestone.
Which is the plate tectonics that is going up for us going down? The subjective, you haven't productive one coming up, correct? What's that one?
That was, when we're talking about the basement rocks, was during that time frame. We're not near a subduction zone right now.
Okay.
So you don't have to worry about being
No,
sucked on.
and then-
If you live in Japan, you'd have to worry about it, but not here.
No, you also have to worry about it in California.
Right.
But when was the last earthquake in this vicinity?
I do not have an answer for you on that one. If we get earthquakes periodically, but they're minor and not associated with any major faults, like the San Andreas, yeah, we don't have that issue here at this time. If they start doing more blasting up at Jerome's, we could have the activation of the Verde Fault, which happened back in the 20s and 1930s.
So my question is about plate tectonics and what is the driver. So we're on this ball, the Earth, and can you tell us a little more about the core of the Earth? What is this turmoil that is pushing and driving, and is it going to be ongoing pretty much for the life of planet Earth?
Correct. It's going to go on for the life of planet Earth. If there's no plate tectonics, then we have to worry. We really do have to worry. But it's all coming from the mantle. You're having you can see in this slide here, you can see the currents. I mean, just like boiling water, you're going to have currents in the mantle because it's all liquid.
So my question is, what's the driver? Is it the gravity of the Earth that is pulling?
The gravity and density of everything coming together.
Mm-hmm, mm-hmm.
Yeah, I don't have any more technical knowledge than that to pass along on it.
And it's a liquid, it's a viscous.
It's a low viscosity, so it's a liquid, yes.
Yeah, yeah. Okay, one more question and
Yeah.
different. Up at the mine in Jerome, what have they taken out of the earth, and are they possibly going to be taking other ores out of the earth? Is it just copper, gold? I don't know.
Okay, so in Jerome, the main driver was copper. There was gold found, there was silver found. It's been said, I haven't seen it in writing, there was enough gold and silver found that it paid for the copper extraction and smelting of it. And all the copper was pure profit for the mine owners. Not for the miners, but that's been depleted. There is still a little bit left. Copper is, if it goes up in price, they might find a new technology at some point to reopen the mines. The mining companies that do own those mines they go into mines periodically, make sure the tunnels are still okay, and the shafts still work. So they're over here on this display on the far right. For the United Verde extension, they go down around 1,900 feet. For the main one, United Verde Copper Company, 4,500 feet. Some of those you can't access anymore because the water tables come up, because they'd had to pump to do the tunnels, and there's no pumping anymore. Any other questions?
I talked to a geologist from Freeport McMoran a number of years ago. He said there's massive gold deposits underneath the copper. The copper was the easy part. And he said in the future, when gold gets to a certain price and environmental laws are relaxed enough, there will be a massive open pit mine to get to the gold that was taken out of Jerome, below the copper. Is there any truth to that?
There is some truth to that. If you look at this complicated VMS deposits slide here, there is an area, let's see if I can find it here. Where is it? Certain parts, I don't see it right now, but certain parts of this hydrothermic vent area would have had more gold than other parts. We had a company in the 1980s called Budge that went back into the United Verde extension mine to try to extract more. Somebody's got binoculars back there. That's pretty smart. We should have passed out binoculars to everybody. But Budge went down to try to reclaim some of the gold down there using a different technology. They spent $35 million recovering that gold. They earned $33 million. So it's a good tax write-off for them. Whether somebody else will come back and do that, I don't know. There's other, I mentioned earlier, there's other ore bodies out in the Black Hills that have been documented. At some point, if the price of copper, gold, silver, zinc, lead go up, they may look into them again. But you got to bring the railroads in again. Back in this time period when they were formed, developed, there was no environmental regulation, so they could just do whatever they wanted willy-nilly. But you can't do that anymore. More questions, please.
I was just wondering, is there anything left in the slag heap? Is there any minerals in there? Is there any traces of gold or silver or anything in the slag?
There's minor amounts. The slag, like we have right outside our window out here, is primarily iron and silica. There was a company, a steel mill was allegedly going to be built here in the late 1950s. They tested that slag, found that they could use that material for their steel mill. However, they couldn't get enough electricity brought in to justify building a plant. So it's still viable for something. The other slag plant over where Clemenceau used to be, not slag plant, slag pile, is being mined by a company using it for asphalt products, like for shingles. And I'm not sure if they're running now. I know they got closed down in 2023 for exceedance of air quality permit. And DEQ had them shut down for a while. I'm not sure if they're back up and running. But there are uses for the slag. Whether it's enough to be justifiable for economic reasons, I don't have an answer to that.
Looking back at your long career in environmental remediation and Superfund sites, what is the current status of the soils and lands that surround the old smelting operations and mining operations around here? And is it closed? Considered clean?
For now, it's considered closed, particularly here in Clarkdale. They had over 600 properties that were excavated over a 10-year period, which ended December of 2024, under what's called the Voluntary Remediation Program. So I'm not sure if that would have been Freeport or was Phelps Dodge still around, but one of the two, they dug up over 104,000 cubic yards of soil in people's yards, down to 6 inches, to remediate arsenic and lead that come out of the smokestacks. Hopefully that answers your question. Okay.
This is a good question to follow that one, I guess. Could you touch on how the limestone and sandstone affects the filtering of the Jerome water aquifer? We're on 5 acres across from the cement plant, and I had our well tested 3 years ago, and it was from a water filtration company, and it was her job to sell me a water filter, and all she came back with was that we had some sediment. So I don't have any knowledge really about how the Jerome water aquifer would be, how the geology affects what minerals might be in the water.
Okay. So if you live in, say if you lived in Jerome, your water's coming from springs over at Mingus Mountain primarily. And that water is good shape. There's no contamination, nothing to worry about there. Down where you're talking about, if you got a well and you've had it tested, that's smart. We naturally have arsenic in the groundwater around here, but not to the levels that exceed the Environmental Protection Agency standards. So if you don't have any problems now, you probably won't in the future, because they would have developed by now. I'm not sure if that's answering your question, because I haven't seen any results of testing of other wells around here, if it's going to be a problem for anyone in the future. But if you have a well, definitely have it tested, the water. Question over here, Mike. I don't know if I heard all the question. There's a microphone going around somewhere right there. But no, I don't have any information about how much they're testing the river. I know the river does get tested periodically For what parameters, I'd have to look that up. I don't know. Can't answer your question on that one. I'm sorry, Michael, I couldn't hear the
Yeah,
lady.
she's basically just saying she's talked to some folks, but I think one of the things that might be good to hear from you is, can you clarify if the slag is inert or is it actually leaching?
I cannot certify that. It should be inert, but should be and are two different things. If they're testing the waters downstream of the slag piles, that would tell you if there's any issue there. And we could probably look that up. I can't confirm or deny anything at this point, though. That's something I would like to do in the future, is come up with a course or presentation on the environmental impacts of the different activities going on in the mines. You had the smelters, they put out the slag, they put out the tailings pond over by Tuzagut, air pollution. There was various things related to that, and I think it would be nice to do a presentation on that at some point.
Yeah, so there was contamination of the soils, so I'm not sure how easily they can prove whether or not the contamination they find downstream is coming from the soils versus
Correct.
from slag or any other place, because
Right.
the remediation program didn't do every square inch of soil.
No.
So I've got a question here from this lady.
You mentioned two separate volcanic periods. One you said was due to subduction. What was the other one due to?
Didn't quite catch all of that. You mentioned you're talking about plate tectonics now?
Yeah, you mentioned two different volcanic periods.
Oh, volcanics. Okay.
Volcanics.
You had the shield type, and you had the pyroclastic.
But
Is it-
the first,
So you have, like House Mountain is a shield volcano.
but what caused it?
What caused it?
Yeah.
It's just magma coming up. There was a vent that opened.
Like was it a hot spot or subduction, that kind of?
It would have been a hot spot.
Okay.
Let's see, which way do I got to go here? See, right here. Here's a hot spot here, and you got some magma coming up, creating a shield volcano. This is what House Mountain would have been. And locally here, we were on a stratovolcano because we were, back 1,750 million years ago, we were in a big caldera that was 6 miles wide that was being fed by the magma coming up from the subduction zone below it. And I equate it, when I give tours up at the Jerome State Historic Park, and I talk a little bit about geology, and a lot of people have a hard time wrapping their heads around 1,750 million years ago. So how I equate it is, if we can condense all that time to 100 years, well then, the ore bodies were formed 100 years ago, but they were discovered 3 minutes ago. So kind of gives you a better picture on looking at the time. More questions? Got two up here.
Where would we find some courses on geology around here?
Good question. There is OLLI program. You familiar with the OLLI program? There should be a geologist doing from Arizona State University called Steve Smenken. He did one last summer over at Clarkdale, Yavapai campus, on the geology of Arizona. And he'll do something, he's told me he'll do something this summer. He hadn't decided yet what. So this is a good place for me to plug my OLLI programs too. I'm going to talk OLLI for a minute. Is there people here that do not know what OLLI is? Okay, we got a couple hands. So OLLI is an acronym for OSHA Lifelong Learning Institute. It was developed back in the Midwest at one of the colleges, I think it was Northwestern University, and there's over 200 universities that have this program now. It's for adults, primarily retired adults, and it's facilitated by volunteers like myself. I'm doing a class coming up, let's see, the first 3 Thursdays of April. The new catalog is going to come out online on Monday. So March 9th, the catalog comes out, and you start signing up on March 11th. And it's cost, I think it's $15 a session. But you can pay, say, I pay $185 a year, and that covers all the classes I want to take. And so if you go on to Yavapai College, you go to their website and look up OLLI, O-L-L-I, and there'll be a web page, one for Prescott and one for Sedona Verde, tilted half graben. And it'll tell you, it's facilitated by volunteers. It could be anything from philosophy to the arts, to sciences, to medical. There's all sorts of things. If you have an interest in something you want to share, that's what the OLLI program's all about. They teach you how to be a facilitator, so you can teach classes, and it's all volunteer on that part. So the classes that are coming up in April, the first one's going to be a deep dive into the United Verde Copper Company and the United Verde Extension. So it's going to be a history of those two companies. The second one, the following Thursday, these will be at 10 a.m. to 11:30. The second one is going to be on the railroads of Verde Valley during the mining period. So we have a fellow named Cody Ely, who's a ranger up at the Jerome State Historic Park. He's going to be leading that one. And I'll lead the third one, which is going to be on the smelters and the process of smelting. So I'm glad you didn't ask me questions on smelting, because I'm still learning. But I'll be ready for the third session of OLLI.
Yeah.
At the college itself, as far as geology, not at this time, no. I mean, you can find things online. The OLLI program has video clips. You can look at old video clips. You might be able to find last summer's program that you can look at on your own, because it would have been via Zoom as well, and they record those.
Could you define the Black Hills, the range of what we actually call the Black Hills?
Can we define it?
Well,
It's part of the Basin Range province. It's the very edge of it, and it would be called a horst or a range, and it goes pretty much from that way to that way.
So
southeast of Camp Verde to northwest of.
So really everything, as you look towards Mingus Mountain, is considered the Black Hills?
That's considered the Black Hills. Mingus Mountain is the tallest mountain of the Black Hills.
Okay, thank you.
Mm-hmm.
This has been very interesting. Do you have some contact information in case someone wanted to touch base with you on something?
I do. If you see me afterwards, I have some business cards I've made up that I can pass out with my phone number, address, email. Yes?
I have two questions.
I got to ask you a question first.
Okay.
Did you get my comment about Reader's Digest version?
Yes.
Okay. Because you seem a little younger than some of our crowd here.
Oh, that's sweet. Thank you. I do have two questions. One is referring to a statement that you had said about Japan sinking. Would you be able to share some of your knowledge about that?
Okay, I didn't catch that one part, the key part. Share knowledge about?
The Japan sinking. Yes.
Why am I not catching this?
Well, you know, we wouldn't
okay.
have...
Japan, okay.
Yeah.
I thought we were talking about Verde. Because Japan is sitting on a subduction zone. And geologically, it's going to go down into the mantle and be assimilated. But that's not going to happen in our lifetime.
No, we're very lucky, yes.
Yeah, I mean, geologically speaking, it's going to be millions of years.
Mm-hmm.
But
that was pretty
that
interesting.
movement is creating all the earthquakes they get over there.
Mm.
And that's the same for Indonesia and a lot of the Southeast Island countries.
Okay.
Hopefully that answered that question.
That was, yes, thank you.
I do have hearing aids, but sometimes they don't work as well as I would like.
My next question goes to, what is your experience with geological hazards or risk assessments?
Geological hazards like landfalls, like
Landfalls,
landslides.
or you know how you put that example of when you're driving, you don't want to be the one looking over to see the what sediment is up in Jerome, or it could be landslides. Maybe you've experienced a tsunami or something similar to the risk that comes with your field.
Okay. I don't know if I can answer that. I don't have any experience really per se on the hazards, physical hazards of when something might give way. That's a good question to ask somebody like for DOT in their engineering department, because they deal with that kind of physical hazards all the time. They would have a hydraulics person that would know from testing, this is going to go within the next 10 years. We have to reinforce this area. But as far as my background, I'm not going to be able to answer that question. Sorry. One more.
I know in Jerome, when they had problems with things coming off, they put up monuments where they could measure the tilt to say when it's going to come down. I used to have an EPA report that, with the tailings below Tuzigoot, in that there was a comment saying that the arsenic there is 33,000 times what's normal in soil. Do you know anything about those tailings? And I just heard recently they're going to remove all that.
Oh, they are. I hadn't heard that. But what happened was when the smelter shut down in 1953, they let the tailings pond pretty much dry out. And so I've seen pictures of it just orange in color with the copper and other minerals in it. And when that dries, the dust gets blown over around. So for a while, Phelps Dodge was watering that to keep the dust down.
We used to four-wheel drive up the end and throw that red dirt all up in there, and we had no idea what was in it then.
No, you wouldn't have known. And then in 2005, 2006, they filled it in with soil and planted what they call native vegetation. But if you stand at Tuzigoot and you look where that area is, it doesn't look native to the plants around here.
Not a lot growing.
But yes, they just filled it in. They didn't excavate. Excavating would be the best remediation. And whether they're going to do that under a voluntary remediation program or consent order, I haven't heard.
Okay, one other thing. Oak Creek Canyon was my playground. I grew up in Oak Creek Canyon.
Mm-hmm.
And when you're going up Oak Creek Canyon, the canyon that goes up Snebley Hill, Old Kasner Cattle Trail goes up there. I hiked it many times as a child. One of those points out there, I found almost what looked like bones, like fossilized bones that looked like marrow in it. Well, I've seen a thing on PBS once that talked about gas tubes, and they fossilized. Do you have any comment on that?
No.
Can I take you there? Can I take you there?
Oh, yeah, definitely. I'd love to see it. But,
well, I'm going to come to Jerome and have a talk with you.
Okay, very good.
I also have a brother who's a historian, has a friend that's a geologist that he called me recently, asked me if there was any Freeport activity because with the prices of metals, he says in the central mine there's a huge ore body that they should be removing right now.
Are you talking about the Verde Central mine?
Yes. That's
been shut down since 1930s?
Well, they opened up during the Depression, yeah.
Okay, that's interesting. I hadn't heard that one either.
Yeah, okay.
Good. See, I learned things.
Well, the same day he called me and asked me this, in the coffee shop in Old Town, sitting next to us was 4 geologists here for something at the cement plant.
Okay.
So what have they found out there?
In the cement plant?
Yes.
Well, they're just digging up red wall limestone, so I'm not sure what they would find other than fossils.
Yeah, okay. That's kind of what they said.
I did read where Mr. Clark was an educated geologist, so he had that to his advantage when he came to Jerome.
Correct.
How was he able to determine so quickly, or however long it took, to determine how much copper was there? Did he see verdigris on?
Well, what happened was Clark, well, he'd been here before. He'd seen the assay work. In fact, he bought out a company back east that did the assay work for the mine up here. And so he knew the quality of the ore. And so when it came up for bidding in 1888, he outbid Phelps Dodge Corporation for that mine because he knew the quality of it. And that's some of the history on that. And with Clark buying that, he had the financial means to do whatever he wanted. He didn't have to have a board of directors or anything. So he put in the narrow gauge rail that went over to Jerome Junction and opened up the valley here, tilted half graben, and everything boomed because of his activities.
I was just wondering, is Jerome still slipping down the hill?
I've been told not, but if they ever started blasting again up there, that could activate the Verde Fault, which happened back in the 1920s and 1930s. But right now it's stable.
Who owns the mineral rights to Black Hill area? Freeport McNamara?
Freeport owns quite a bit of it. There's going to be some Forest Service up there. I don't know if there's private holdings other than that. I mean, you can go online, look at claims maps. They're pretty darn detailed, and I haven't done that. Any more questions, comments, snide remarks? I'll take anything.
I just wanted to make a quick comment because I've always tried to wrap my head around very large numbers, and so I came in right when 4,600 million, I don't know, how much is it?
Right.
Anyway, something that has helped me is to understand that 1 million seconds is about 12 days. 1 billion seconds is 32 years. So I did the math, and you can correct me if I'm wrong. I just turned 69, so that's about half in tick-tock, 1 second, that's about half of the Earth's age, I guess. So 147.2 years of seconds, if you're thinking about, like when time goes really slowly, like when you're missing your child or you're in pain or something, that's a long time. So it helps me wrap around big numbers.
Okay, good, thank you. Thank you for sharing.
Any other questions?
Okay. We got a question over here.
On the ground, where is the Verde Fault?
On the ground?
No, I mean, from us
traversing
the surface, where is the Verde Fault?
Physically, would have run right through the town of Jerome. So if you're standing at the Douglas Mansion and looking at the town of Jerome, do you know where the third hospital is, which was turned into the clubhouse? It's a yellow building up on the hill. So behind that was a wing that got destroyed because it was over the Verde Fault. And if you look to the left of that, over to Jerome Grand Hotel, which used to be the fourth hospital, and you come down below that, you'll see what used to be the original elementary school, which is now Town Hall up there. Between those two buildings was the high school, and that was built over the Verde Fault. And when that got activated, the fault got activated, that crumbled and had to be torn down. So that's basically it runs, and it runs up through the open pit mine area and then wraps around Mingus Mountain, going down the valley.
So basically is along the face of what we're looking at?
It's on the face of the hill, yeah.
Yeah.
It's not like it's at the bottom of the hill. It's about midway up.
Okay. Thank you.
Mm-hmm.
Hands?
Hi, just to clarify, these minerals and ores that they're mining are formed at the fault?
No, they're formed at the where the subduction zone goes and taps in the mantle, and you're getting the magma coming up, and that's where the ore bodies are being formed, at that location to the far left in that slide.
So the fault has nothing to do with the subduction zone?
No, the fault came later. This is 1,750 million years ago. The fault came around 20 million years ago.
Okay.
So there's a big time gap, and that's what exposed the ore bodies so they could be found.
Any last questions?
A few years ago, I spoke to a miner from Freeport McMoran that told me that fault line in the ground is moving today, and they're hoping within 20 years Jerome goes away so they can mine the mountain.
Okay. Can't say I've heard that, but very good.
Okay, I'd like to thank Hal for his presentation.
Thank you.
And I'd also like you to visit our museum, which is open this morning. We have a very nice geology exhibit with a lot more rocks. The exhibit was put together several years ago by Paul Handverger, who is a geologist that used to work for Verde Exploration.
Very good.
Okay. Thank you.
Thanks everyone for coming.